You know, you probably use GPS pretty much every single day without a second thought. But have you ever stopped to wonder how we go from getting you sort of close to a location to pinpointing a spot with millimeter precision? I'm talking about the kind of accuracy surveyors and scientists need. Today, we are going to dive deep into the incredible tech behind satellite positioning. All right, let's jump in. So, yeah, how do we make that leap? How do we get from the 10-meter accuracy of your phone, which, is perfectly fine for finding a coffee shop, to the centimeter level precision you need to build a bridge or, get this, even monitor the slow crawl of tectonic plates? The difference is it's staggering. And the secret? Well, it lies in a few incredibly clever techniques. At its very core, the whole thing is about one simple goal: positioning. Whether you're standing still or flying down the highway, the entire Global Navigation Satellite System, or GNSS, is built to answer one fundamental question: where am I exactly? Now, the basic idea for finding that position is this classic geometry concept called trilateration. So first, your receiver measures its distance to one satellite. That puts you somewhere on the surface of a giant invisible sphere. Then you add a second satellite. Those two spheres intersect, and now you're somewhere on a perfect circle. A third satellite narrows your position down to just two possible points. And honestly, one of them is usually floating way out in space, so it's pretty easy to figure out which one is you. So, you're probably thinking, okay, 3 satellites, we're done, right? Well, in a perfect world, yes. But in the real world, there's this crucial fourth dimension we have to solve for: time. See, the clocks on the satellites are mind-bogglingly precise atomic clocks. Your phone's clock, not so much. Even a tiny, tiny error in timing can throw your calculated location off by miles. So, and this is the key takeaway, we need to see at least 4 satellites to solve for our 3D position and that critical time difference. All right, so now that we've got the basic concept down, it turns out there are 2 fundamentally different ways to go about this. You can either try to figure out your location all by yourself, or you can use a buddy system. Let's break down what that really means. Over on the left, you've got point positioning. This is what's happening in your phone or your car's navigation system. There's just one receiver, working alone, figuring out its absolute position on the globe. It's great for getting around town, but the accuracy is typically somewhere between 10 and 30 meters. But then, on the right, you have relative positioning. This is the pro-level stuff. It uses 2 receivers, a stationary base at a location that's known down to the millimeter, and a moving rover. By working together, they can get down to centimeter-level accuracy. It is a complete game changer. Okay, so we've got these 2 methods of positioning, but how does a receiver actually measure the distance to a satellite that's thousands of miles away? It's not like there's a giant tape measure stretching into space. The receiver uses the satellite's signal as a kind of ruler. And just like with positioning, it turns out there are 2 different kinds of rulers we can use. And the difference between these 2 is really where things get interesting. Pseudo-range is what your phone uses. It basically times a digital code that's embedded in the signal to figure out the distance. It's simpler, for sure, but it's kind of like using a stretchy, not-so-accurate measuring tape. It'll get you meter-level accuracy. Carrier phase measurement, though, that's like using a ruler with millimeter markings. It measures the phase of the radio wave itself, which gives you incredible precision. But, and this is a big but, it comes with a massive puzzle that you have to solve first. And this is where the real magic happens. To get that jaw-dropping, centimeter-level accuracy, engineers combine the best of both worlds. They take the buddy system of relative positioning and pair it with that ultra-fine ruler from the carrier phase measurements. So here's how it works. You've got that base station, and it's sitting on a point with coordinates that are known with absolute precision. Now, it's looking at the exact same satellites as the rover at the exact same time. And because it knows precisely where it is, it also knows what the signal travel time should be down to the nanosecond. So, the base station compares the signals it's actually getting with what it knows it should be getting. That difference? That's the error. It's all the tiny delays and distortions caused by the atmosphere or satellite clock drift, you name it. The base station calculates all of these errors in real time and then packages them up into a correction message. And this is just brilliant. The rover gets that correction message from its buddy, the base station, and immediately applies it to its own measurements. Since the 2 receivers are pretty close to each other, they're experiencing almost the exact same atmospheric and satellite errors, so applying the corrections essentially cancels out all of that noise. It's like giving the rover a perfect, error-free signal. And the result? A position that's accurate to within about 1 centimeter. Just stop and think about that for a second. We've gone from a 30-meter blob of uncertainty down to something the width of your thumbnail, all just by having two receivers talk to each other. It's incredible. But even with this incredibly powerful technique, it's not quite a done deal. To maintain that amazing precision, there are two final, very tricky puzzles that engineers have to constantly solve in the background. So that first hurdle is something called a cycle slip. Remember that superfine ruler we were talking about, the carrier phase? Well, a cycle slip is what happens when you temporarily lose the signal and your receiver essentially loses its count. It's this sudden, jarring jump in the measurement that can completely wreck your accuracy if it isn't caught and fixed right away. And what causes these things? Oh, all sorts of real-world stuff. Driving under a bridge, walking past a tall building, a weak signal from a satellite that's low on the horizon, or even just a weird software glitch. Any of it can cause the receiver to lose its lock and create one of these cycle slips. But honestly, there's an even bigger, more fundamental mystery we have to deal with. See, the receiver is fantastic at measuring the phase of the radio wave that's hitting it right now, that last tiny fractional part of the wave. But it has absolutely no idea how many millions of full, complete waves traveled all the way from the satellite to get there. It's kind of like knowing the exact length of the last bead on a very long string, but having no clue how many beads are on the whole string. This mystery has a name: integer ambiguity. And it is, without a doubt, the single biggest challenge in high-precision positioning. It's that unknown whole number of wave cycles between you and every single satellite. Finding that exact integer, that's the final critical key that unlocks the highest possible level of accuracy. And hey, don't just take my word for it. The people who live and breathe this stuff put it perfectly. Achieving this kind of accuracy is completely 100% dependent on being able to solve this puzzle. Resolving that ambiguity is everything. It's the moment the fuzzy picture snaps into crystal clear focus. So the next time your map app guides you flawlessly to some new address, just take a moment to think about the incredible, invisible dance that's happening behind the scenes. It's a dance of trilateration, relative corrections, and the constant solving of these unbelievably complex signal puzzles, all to answer that one simple question: where are you? With an accuracy that is truly nothing short of extraordinary.